Nice great everyone, and thank you for the kind invitation. As chairman said, I'm Vesna Ocelić Bulatović, and I come from the University of Zagreb. I'm very pleasure to be part of this conference today, to have a lecture. I'm sorry that I couldn't come to the beautiful capital of the Italy because of my commitment. My lecture today is related to biodegradable polymer materials, which are under increased research by many scientists considering the problems we face today. We must be aware of the importance of the moving from a linear economy to a circular economy with an emphasis on plastic waste. So the title of my lecture is shown, and the chairman said, biodegradable material is a key factor of the circular economy. The content of my lecture today will be related as shown in this slide, a brief introduction to the linear and circular economy and face of plastic waste. Then some things about biodegradable materials, as I love to say, materials of the future. And I will give a brief overview of our research relating to biodegradable blends of low density polyethylene and thermoplastic starch. And finally, I will highlight some conclusions of our research. Linear economy, as we know, this is the traditional model where raw materials are collected and transformed into products that consumption use until discarding them as waste, with no concern for their ecological footprint and consequences. Products and materials are generally not used to their full potential in a linear economy, and as the name suggests, always move in one direction, from raw materials to waste. We can point out that linear economy is focused on profitability. What's the consequence of the linear economy? The consequence, this is a polluting system that degrades natural system and is driver of global challenges, including climate change and diversity loss. On the other hand, when we talk about circular economy, in circular economy, the emphasis is that production must have a little impact as possible on the environment by leaving less of the footprint. To be sustainable, it must follow these three principles: reduce, reuse, and recycle. Design, production, and consumptions have to be based around sustainability. Production must keep energy consumption to the minimum, using renewable resource and not polluting raw materials. Projects must not have a limited shelf life and be built so they can be repaired or recycled. The key difference is that, as I said, for the linear economy, is focused on profitability in respect to the product of life cycle, where the circular economy targets sustainability. A transition to a circular economy is crucial to allow us to drive in the future. Plastics, when plastic was discovered long ago, it was a revolution in materials, and its property lasts forever, was something that changed the world, and plastic became materials #1. Today, we cannot imagine life without plastic, but their non-degradability, as well the trend of the linear economy, has led to major problems. The accumulation of plastic waste and major environmental pollution. That's why we must continue the shift from linear to circular economy to make sure society progresses in a way that is environmental friendly. Therefore, it is extremely important to replace conventional plastic with biodegradable plastic. What we can see on this slide on the left of this slide is global plastic production and accumulation of plastic and future trends. As we can see, the global production of plastic materials increased tremendously from 1.5 million tons in 1950 up to 400 million tons in 2020. Projections are that in 2050, plastic production will double compared to 2020. Also, if we see on the left side, on this cookies pie, we can see that large amount of the plastic production is relating to the plastic packaging. Also, the largest amount of plastic waste is related to plastic packaging. Most of the, as we know, most of the packaging in use once, resulting in the daily formation of large amount of plastic packaging waste. We can also see from this pie that the large amount of plastic waste ends up in landfill. That's only 24% is recycled. Also, when we see on this slide, the plastic waste accumulation problem is becoming a more urgent issue for societies and nations across the world. The collection recycling rate of plastic waste is alarmingly low in all countries, and most of the waste is sent to landfill. This red on this graph. And incineration ultimately ends up as litters on land or in the ocean, causing contamination of the environment. In circular economy, zero landfill is needed to achieve the circular economy related with plastics. The circular economy consider every stage of product journey before and after it reach the customer. This approach is not only vital to stop plastic pollution, it also offers strong economical, climate benefit, and social benefit. What we can do? We must change how we design, use, and reuse plastics. We cannot simply recycle or reduce our way out of the plastic pollution crisis. If we don't act now, as we know, by 2050, there could be more plastic than fish in the oceans. To create a circular economy for plastic, we must take three actions: eliminate, innovate, and circulate. Eliminate all problematic and unnecessary plastic items. Innovate to ensure that the plastic we do need are renewable, recyclable, and biodegradable. And circular all the plastic items used to keep them in the economy and, what is very important, out of the environment. This brings us to the importance of the increasing use of biodegradable plastic as a packaging material. Biodegradable plastic decompose naturally in the environment. Decompose in the natural compounds such as water, carbon dioxide, and other decomposition production consumed by microorganisms. They are derived from natural sources, corn, sugar, and so on. And what is important is less harmful to environment than traditional plastics. The emphasis of this lecture is on thermoplastic starch, a completely biodegradable polysaccharide. Starch has gained a lot of attention as a biodegradable plastic due to its natural biodegradability in wide range of environments, low cost and easy availability. It's produced industrially by isolating from plant materials, most of the potatoes, corn, rice, and so on. But native starch is not a thermoplastic material. The problem with native starch is that the melting temperature of the starch is close to the decomposition temperature of the starch. So natural starch must be modified in order to be processed by classical processing methods that we use when we use for the production of the conventional plastics. Method of the modification of natural starch is plastification with additional plasticides, water, glycerol, and so on. In this slide, we can see the plastification process of the starch. Conversion of starch into thermoplastic materials requires the breaking of the granules, the amylose structure units, by applying the mechanical shear stress and heat in the presence of suitable plasticides, as I said before. The starch plastification resulted in completely destruction of the crystal units, mainly amylopectin, resulting in a completely amorphous polymer. What's the rule? The rule of the plasticide is to get between the polymer chain, reducing the intermolecular interaction between starch molecules, and increase the flexibility of natural starch, and leading to a more processability of the starch. But wider application of thermoplastic starch compared to synthetic conventional polymers, plastics, is limited due to their weaker functional properties and difficult processing, high hydrophilic, poor mechanical thermal properties. But these problems can be overcome by development of new blends, by blending thermoplastic starch with other polymer to obtain materials with the required properties. As we know, low density polyethylene is well-known conventional plastic, synthetic plastic, that is widely used in daily life due to its excellent properties. Polyethylene is one of the most dominant plastic packaging materials. As we say, as we can see on this slide, it's many advantages of the low density polyethylene, but main problem with plastic packaging with polyethylene is that is thrown uncontrollably into the environment after use, generating a large amount of plastic packaging waste every day. Polyethylene has become one of the major resources of environmental pollution. As I said before, the blending polymers is the most effective way to obtain materials with the required properties. So, if we blend in conventional polymer with thermoplastic starch, is a significant way to overcome the limitation on individual materials of the thermoplastic starch and low-density polyethylene. Also to improve the weak mechanical or thermal property of TPS, while on the other hand, the biodegradability of such blend is enhanced. Our research, the aim of our research is to obtain environmentally friendly and economical, it's very important, economical materials, biodegradable blends with low density polyethylene and thermoplastic starch. Because of the highly hydrophilic character of TPS and hydrophobic character of PLD, polyethylene, the use compatibilize is an essential step. Why? The role of the compatibilize is to reduce the interfacial tension between the polymers in order to achieve fine dispersion of one phase to the other, which resulting in improving processing and application properties of the final materials. In our case, in our research, the compatibilized was graph copolymer of polyethylene with maleic anhydride. Why? And we can see on this structure of the compatibilized, the grafted maleic anhydride is hydrophilic part, hydrophilic part to TPS, and polyethylene is hydrophobic part that's love the polyethylenes. This is on this slide. This is the material that we use in our research. We use wheat starch that was plasticide with glycerol. The amount of glycerol was 40%. This is the preparation of our polymer blends. First of all, we have to prepare the thermoplastic starch with glycerol, and then we prepare the blends with and without the compatibilized. The proportion of thermoplastic starch was from 10 to 50%. And the content of the added compatibilized was 3%. On this slide, we can see all the methods, the material characterization that was carried out on the test polymer blends with PELD and TPS, with and without the compatibilized. And in this lecture, we will only touch on some of the results. We do morphological structure, thermal properties, barrier properties, and mechanical properties. Also, we investigate the biodegradability during composting process in the period of 16 days. And on this slide, we can see the schematic diagram of composting process. We move on the results and discussion of the selected results of our research. On this slide, we can see the morphology, the same micrographs of native wheat starch on the figure A. As we can see, the native wheat starch has a granular structure. This granular structure, these granules are spherical, oval, and have various sizes, which are prone to agglomeration. During the plastification, they occurred a transformation of granular morphology into homogeneous polymeric film. We can say that the thermoplastic starch was obtained. Hello, sorry. Morphology of the fractured surface of TPS, as we can see, it's smooth, clear, homogeneous structure due to good dissolution of starch particles after the plastification of the process. In this slide, we can see the same micrographs of polymer blends with low and high content, without and with the addition of compatibilized. Without compatibilized, we can see that PELD and TPS phases were incomparable. They create two-phase morphology in which the particle domains of TPS are dispersed in PELD matrix. Cavities are evident as a consequence of pulled out TPS particles, which indicating weak interfacial adhesion due to the hydrophilic character of TPS and hydrophobic character of PLD. The higher content of TPS phase in the blend illustrates pronounced two-phase morphology, as we can see on these SEM micrographs. Compatibilized blends displays reduced dispersed phase size arising for coalescence suppression, and interfacial tension decreases, indicating better compatibility of TPS and PLD phases. It is also evident that the finer homogeneous film was with added of a small proportion of TPS with comparison with the addition of large proportion of TPS, where the TPS agglomeration is formed that we can see on these SEM micrographs. On this slide, we can see the results of thermogravimetric analysis, DTG curves of the blends with the compatibilized. The thermal degradation of the blends show two-step decomposition process. The first steps is related to the first step of degradation at low temperature was related to the degradation of TPS, while the second step of the degradation corresponds to the degradation of PLD. Extreme thermal stability of PLD contribute to increase the thermal stability of TPS in polymer blends. The incorporation of compatibilized thermal stability has increased, as we can see, confirming that positive effect of compatibilized on the thermal stability on the investigation plans. This slide shows the results of the water vapor permeability as barrier properties, WVP values. As I said, as important properties for polymer packaging materials. As I expect, hydrophilic thermoplastic starch show extremely high value of water vapor permeability, where hydrophobic PLD shows very low value, as we can see. Also, increase the WVP values increase with higher TPS contents, and this increase is attributed to the hydrophobic nature, but also it's related with linear morphology that we saw in the SEM micrographs, which provides pathways for moisture to penetrate the voids and be retained, then absorbed by TPS. The compatibilized lowers the WVP values of the blend by acting as a bridge between PLD chains and TPS, allowing better introduction between the phases. In general, packaging materials must have good mechanical properties, such as elongation and break. The mechanical properties of tension, strength, elongation, and break of both compatibilized and uncompatibilized blends with different amount of TPS are shown in this slide, as we can see. Tensile properties of polymer blends were significantly affected by the percent of content of TPS. It can be seen that both The compatibilized and uncompatibilized blends show a continuous decrease in elongation and break with increasing loading of TPS. From picture, it can be seen that the addition of compatibilized improved the mechanical properties up to 30% of adding a TPS. We can conclude from the mechanical results that the addition of compatibilized has a positive effect on the mechanical properties of the blends. On this slide is the table relating to the result of change of mass for the blends during biodegradation test under composting condition. Poor polyethylene show no mass loss during the 16 days period of the composting process. TPS was completely degraded during this process because they are very hydrophilic and serve as food for the microorganism. In the composed, the microorganism recognize the carbon bonded thermoplastic starch as a good source of nutrients. By blending with PLD, the biodegradation rate of the blends increases. TPS is more easily attacked by the microorganisms than PLD. When the content of thermoplastic starch is low, the weight loss is small, but at the TPS content increase, a significant weight loss is observed for both polymer blends with and without the compatibilized. The TPS degrades rapidly, creating cracks that facilitate microbial access to either fully or partially biodegradable components in the blend. When the starch is removed, the polymer matrix loses its structural integrity, allowing further access for microorganisms and promoting the biodegradation process. On this slide, we can see the presented morphology of the sample before and after composting, monitored by light microscope. On LM micrographs, evidence that blend with and without the compatibilized up to the 20% of TPS were compact with minimum degradation. In contrast, the blend with high TPS content were completely degraded during composting process of 60 days. For low TPS loading, TPS particle maintained within olefin matrix with slowed down degradation. We can say for the high loading of 50% of TPS, a continuous polysaccharide phase was formed, enabling completely degradation. And we come to some conclusion of our research. And we say a good dispersion was achieved from low TPS content, but agglomeration of the starch particles occur in presence of high amount of TPS. In the presence of compatibilized in the blends, have better thermal stability, mechanical air barrier properties. This research emphasizes the importance of biodegradable materials based on thermoplastic starch as a new generation of materials with low cost and enhanced biodegradability. It is important to know that the use of this blend is extremely important in reducing the environmental impact causing by indiscriminate use on conventional plastic in the packaging. The challenge with these materials is to find a balance between good biodegradability and mechanical performance at a reasonable cost. For certain blends, the balance performed could be confirmed. However, there is still many disadvantages of such blends, and further studies are needed before using such blend as active packaging. Okay, thank you. Thank you for your attention. And if I was